Hi, in this video we will solve some examples of evaluating definite integral. Specifically, the examples we have will involve a function, piecewise defined function, and to evaluate these integrals we have to first apply some properties of definite integral, break the integral to smaller integrals, and then use the fundamental theorem of calculus. Let's see how this works. Well, here, absolute value of x, remember that absolute value of x is a function which is piecewise defined. For x is bigger than 0, that gives us x back. For x is negative x's, we have to multiply another negative sign to get positive value of that. As you see, there is no antiderivative for this function, though there are, each piece has its own antiderivative, and we can find each one of those ones. What we need here to do, first apply the property of definite integrals, that we can break the interval of integration to smaller pieces. So I go from -1 to 0 and from 0 to 2. But when we are on the interval -1, 0, the number is negative, and absolute value of x is defined by -x. And on the interval 0 to 2, it is just x itself. Now, use fundamental theorem of calculus part 2 for each one of these. I know that an antiderivative of negative x is minus x squared over 2, and we need to go from -1 to 0. Then antiderivative of x is x squared over 2. We go from 0 to 2. And this gives us -0 squared over 2 minus -1 squared over 2 plus 2 to the power 2 over 2 minus, so now I'm applying fundamental theorem of calculus for the second one, 0 squared over 2. So these two are 0. Here what we have is 1 over 2 plus 4 over 2, which altogether is 5 over 2. Okay. How about absolute value of cosine x? Well, remember that cosine x, well, we have the graph of cosine x, yes. So it goes like this. At pi it is 0, then at pi over 2, is 0, at pi is -1. So here, then you notice that cosine is positive on the interval 0 to pi over 2. And from pi over 2 to pi, it is negative. Why is it important? Because there's absolute value. And absolute value makes the function piecewise defined. To be able to evaluate on each part, we have to make sure that we get rid of absolute value first. So to do so, we go from 0 to pi over 2, where the cosine x is positive, and the other piece, which is from pi over 2 to pi, we have to have, so I just applied the property of definite integral. Now, the absolute value of x on this interval, 0 to pi over 2, is just itself, because it is a positive number. But on this interval, cosine x is a negative number, as you see in the graph. So the absolute value needs to multiply the cosine x by another negative sign to get a positive number out. Now we have fundamental theorem of calculus part 2. What is antiderivative of cosine x? Is sine x. Go from 0 to pi over 2 plus antiderivative of negative cosine x is negative sine x. Go from pi over 2 to pi. And well, now apply the upper value minus lower value plus negative sign of pi minus negative sign of pi over 2. As you see, okay, so sine of 0 is 0, sine of pi is also 0, sine of pi over t is 1, and sine of pi over 2 is 1 also here. So there's negative, negative plus 1. Altogether, that gives us 2. And the last example, we have piecewise defined function, and now we want to integrate 0 to 2. When it is this interval, we don't know how to deal with it because each piece has its own antiderivative. So first thing to do is to break the integral into 2 pieces such that I can use each one of these formulas given for f on the separate integrals. So 0 to 1, 1 to 2 of e to the okay, sorry, I just want to write, okay. Now, in the interval 0 to 1, we are on this part of the domain, so the function is x squared minus x. Well, here I'm using variable t, so I have to write everything in terms of t. T squared minus t dt plus from 1 to 2, it is e to the power t plus 1 over t dt. Now I have to find the antiderivative of each one. Here I have t cubed over 3 minus t squared over 2, go from 0 to 1, plus antiderivative of e to the power t, and 1 over t is derivative of ln t, so we go from 1 to 2. And the values are 1 cubed over 3 minus 1 squared over 2 minus 0 cubed over 3 minus 0 squared over 2 plus e to the power 2 plus ln 2 minus e to the power 1 plus ln 1. Here, this is 1 over 3 minus 1 over 2 minus 0 plus e to the power 2 plus ln 2 minus e, and ln of 1 is 0, so that will be minus 0. And well, that's the number we were looking for. Well, you can make it 1, well, I will write different things here. So for example, 1 over 3 minus 1 over 2, it is 2 minus 3 over 6, which is negative 1 over 6, plus e squared minus e plus ln 2. So as you saw in all these examples, when the function is piecewise defined, we first use the property of definite integrals, break it to small pieces such that on each piece we have one definition, one formula for the function, and then apply fundamental theorem of calculus.